So what's up, guys? Welcome to Venom Pranav Academy, and in our today's video we are going to look at set builder notation. Previously we looked at the four methods that we use in set representations, of which set builder notation was the second method that we looked at. Now in this video we want to look at several examples and to take into consideration all the factors and all the requirements that are expected of us in as much as we are representing sets using this method. So remember, when we started set theory, I told you to say there are certain things and there are certain symbols that are very much imperative for the study of mathematics, and some of those symbols are simply going to be used under this method. Okay, so let's look at some examples. Let's suppose we've got a given set A. Okay, A is our given set, and we are going to simply write this set in roster form, and we've got elements. These are the given elements. Okay, it's a finite set, and they've told you to say represent this set in, or present this set in set builder notation. Now you remember that you're going to get A because for both roster form and set builder notation, they are simply both of the methods simply uses the curly brackets. Okay, so you're going to get the set A. Okay, now when you get the set A, what do you realize? You know that in this set there exists an element. Okay, it can be elements or just an element, but you know that there is an element. Let's take one particular element, and that element we are going to call it X. If you want, you can call it Y or V or W, whatever letter you prefer. Okay, now if that's the case, then we know that X exists in the set A. Okay, now as this X is existing, there are certain things that we need to know about this X. So this X is such that, okay, and I told you to say such that can be represented by two things. It's either you say you use this symbol or you use this symbol. So we know that in the set A we've got an element X, and X is such that, okay. Now this notation that we want to write, that we want to bring about, is going to give us a description of the element X that we are having in the set A. Okay, now what can you say about these numbers? We've been given 1, 2, 3, 4, 5, 6, and we know that all these numbers belong to a set of numbers that we call natural numbers. Remember, we looked at sets of numbers and we said natural numbers are simply counting numbers starting from 1 all the way up to positive infinity. Okay, so 1 all the way up to 6, we know to say these numbers belong to a set of natural numbers. Okay, but then what is the range of this element X that we have? So we want to find where the X is starting from and where X is ending from. So if you want, you can simply say X is such that X is what is less than or equal to 6, and X is a member of natural numbers. Okay, this is one of the ways in which you can represent this set. So what does this mean? It means that in the set A you've got an element X, and X is such that it is less than or equal to 6, and X is a member of natural numbers. Now this last part comes to describe what we are dealing with, because if I didn't put this part, then we've got a lot of numbers that are less than 6. But the moment I say that X is a member of natural numbers, then you realize to say natural numbers are counting numbers, and we are going to get all the numbers that are less than or equal to 6, and these numbers should be natural numbers. So those numbers are going to be 1, 2, 3, 4, 5, and 6 itself, because we are saying less than or equal to 6. But this is not the only way. Another person might choose to write it like X is such that 1 is less than or equal to X less than or equal to 6, and X is a member of natural numbers. Now, do you understand that this expression is also correct? Very much correct. Okay, because we are saying that the elements should start from 1. Okay, they should include 1, and they should also include 6. So all the numbers between, this is the limit that we've given, all the numbers between 1 and 6 represent element X. Okay, but these numbers should be a member of natural numbers, because we know that there are a lot of numbers existing between 1 and 6, such as 1.01, but that 1.01 is not a natural number. So we are specifically looking at natural numbers. Okay, so these are some of the ways. Another person can simply say X is such that X is less than 7, and X is a member of natural numbers. We know that natural numbers less than 7 are simply 1 up to 6. Okay, so this was the first example. Let's look at the second example. The second example is not going to be so fair. I want us to look at this. Let's assume we've got another set B, and this B contains of elements 3, 6, 9, 12, and 15. Okay, so this is in roster form. So now how can you represent this set in set builder notation? So you look at the numbers, And if you look at the numbers, you evaluate the numbers, you realize that all of these numbers are multiples of what? They are multiples of 3, such that when you're opening this set in set builder notation, you are going to say that 3x is such that, okay, then you describe what x is, because you know that they are multiples of 3. So the first thing you do is you first equate the 3x. For you to get the limit, you equate the 3x to the first number and the last one. So you equate it to 3 and find the value of x, okay? So x is simply going to be equal to 1. So you know that 1 is less than or equal to x, okay? Then you equate 3x again. This 3x, you equate it to the last thing, which is 15, the last element. When you divide, you get that 3 into 15, you get 5. So it's also going to be less than or equal to 5, okay? And this x is a member of natural numbers, because 1 and 5 are simply members of natural numbers. Then you realize that when you list that the natural numbers existing that are greater than or 1 but less than 5, you're going to get 1, 2, 3, 4, 5. And if you are going to multiply all of these numbers or elements with the 3, then you realize, because these are representing x. So if you say 3 times 1, you get 3. 3 times 2, you get 6. 3 times 3, you get 9. 3 times 4, you get 12. 3 times 5, you get 15. So that's how you are going to represent this set. If you want this expression, you can simply change it. You can simply say 3x is such that x is less than or equal to 5, and x is a member of natural numbers. Okay, you know that natural numbers less than or equal to 5 are simply 1 up to 5, including 5 itself, because we are saying less than or equal to 5. And when you slot them here, it simply meets and gives us back the set in roster form. Okay, so this is how you are going to work or to look at the numbers. Another example that I want us to look at is simply going to be, let's say we've got set C, and this set is contains elements 2, 4, 6, 8, and 10. Okay, now what do you realize about these numbers? You also realize that all these numbers are simply going to be multiples of 2. So just like the previous one, this is going to be 2x is such that x should be less than or equal to 5. Okay, because when you equate 2x to 10, you get 5, and x should be a member of natural numbers. Okay, and you realize that when you put 1, you get 2. 2 times 1 is 2. 2 times 2, 4. 2 times 3, 6. 2 times 4, 8. 2 times 5, 10. You get back the set, but others can write it as x should be 1, and x should be a member of natural numbers. This also stands. Okay, the fourth example that I want to look at, let's assume we've got the set D, and this set contains elements 1, 4, 9, 16, and 25. Now, I want you guys to notice something about these numbers. When you look at these numbers, you realize that this set in roster form is simply possessing elements that are perfect squares, okay? And we said that perfect squares are simply numbers, simply a product that you get when you square a number by itself, or simply when you multiply a number by itself, or when you square a specific digit. So now what are you going to do to represent this in set builder notation? So D is going to be equal to x squared such that, okay, such that now, well, if you've got a square there, what do you think you're going to do? You're simply going to equate x squared should be equal to 1, okay? You introduce the roots this side. What is the root of 1? It's simply 1. So it's going to be 1 should be less than or equal to x. Then here we're also going to have less than or equal to x. You also equate it to the last part. So what is the root of 25? The square root of 25, you realize that it's going to be 5. Then x should be a member of natural numbers. Okay, this notation is going to give you the set that we have up above. Apart from that, you can simply say x squared is such that x is less than or equal to 5, and x is a member of natural numbers, and this is also going to stand. So what is the catch? The catch, guys, is you simply pay attention, or you notice the pattern of the numbers that you've been given in roster form. Okay, sometimes they're not going to give you in roster form. They're simply going to tell you to say write a set of numbers, or prime numbers, or let's say even numbers that are greater than 2 but less than 10, and represent that set in set builder notation. So you simply have to first understand and write that set in roster form, then understand and look at the pattern of these numbers, then represent them by looking at how these numbers are occurring, represent them properly using a proper notation, and please always try. You're supposed to try out all the numbers and see if it's going to give you the elements that you got in the roster form that you formed before you started changing the representation and using set builder notation. That is very vital and very pivotal. So we are going to look at probably the last example. Let's say you've got elements, you've got set E, and set E contains elements -3, -1, 1, and 3. Okay. Now, if you look at these numbers, what can you say about these numbers? Okay. Remember, guys, we looked at sets of numbers, and that was for a particular reason. And that reason is simply what we are witnessing now. You should be able to identify what numbers you have, even in a given set. When you're given elements in a certain pattern, be able to figure out to which set those numbers belong. Okay. So here, we probably have numbers belonging to odd numbers, to a set of odd numbers. We've got -3, -1, 1, and 3. Remember what we said about odd numbers. We said these are numbers which, if divided by 2, are simply going to result into a fraction. Okay, so these numbers, or this set, can be represented in set builder notation. If you understand to say these are odd numbers, then you know that odd numbers and even numbers only differ by 1. Okay, so what you are going to do is you are going to say 2x plus 1. Okay, so in short, you are going to say E is going to be 2x plus 1 is such that, okay, now you're looking for the limit. So you say you equate this 2x plus 1, you equate it to the first element, which is -3. Then you solve. 2x is simply going to be equal to -3 minus 1. So 2x is simply going to be equal to -4 over 2 over 2. What do you get? X should be equal to -2. Okay, so x should be equal to -2 as your first element. So you put -2. Okay, then should be less than or equal to x. Then this should also be less than. Then you equate 2x plus 1, you equate it to 3. So what do you get? 2x should be equal to, this goes the other side, so you get 3 minus 1, which is 2, over 2 over 2. So what do you get? You get 1. Okay, and x should be a member of natural numbers. Okay, then you can put like this. So now, does this expression give us what we are expecting? Let's say we've got -2. So in roster form, or what they are telling us, we've got -2, -1, we've got -2, -1, and if we are looking at, oh sorry, this should be a member of odd numbers. Rather, if we look at these numbers, and if we put -2 here, what do we get? We get -2 times 2 plus 1, which is -4 plus 1 gives us -3. If we put -1, what do we get? We get -2 plus 1, because if we say 2 times -1, we get -2. -2 plus 1, we get -1. If we put 0, what do we get? If we put 0, then we are going to get 2 times 0, which is going to give us 0. 0 plus 1, it gives us 1. If we put 1, what do we get? 2 times 1, it's 2, plus 1, it's 3. So you realize that this notation and these limits that we've put here give you the entire elements that you have in the set of odd numbers. Okay, so you remember that x should be a member of odd numbers, because in natural numbers we don't have a 0. In natural numbers we also don't have a negative numbers. Okay, but if you want, you can simply say it's a member of integers, because integers are simply positive or negative whole numbers. Okay, and remember we said that all the numbers that you are going to think of are more than likely to be integers, because negative or positive number is going to be an integer, provided it's a whole number. Now, I want to talk about something. There are certain sets that you are going to be given, and those sets, guys, just can't be expressed in set builder notation, as in you can't come up with a limit that you are going to use to describe those sets. Okay, so what I want you guys to is, what I want you to realize that there also exist certain sets that you just can't have a notation that you are going to use to represent in set builder notation. Sets like, let's say, set A contains elements okay. Now you realize A, E, O, U. That's what you have. How are you going to represent this in set builder notation? So you can only say A is such that A possesses an element X, and X is such that it is a member of a vowel. Okay. There is nothing that you can do to represent this setting by forming limits. Okay. Then let's say you've got a set B contains elements 2, 3, 5, 7, 11. You realize to say there is no pattern that you can come up with to describe these numbers. So you simply use words. If there's no pattern, if there's no way of representing a particular set into set builder notation using limits, then you use words. But most of those scenarios, or most of the questions that you're going to encounter, there's going to be a way of representing using limits. But in such type of instances, you simply say b should be equal to x is such that x is a member of prime numbers, because remember, these are prime numbers. Prime numbers, they only have two factors, that is 1 and the number itself. And remember, we said 1 is not a prime number. Then you give the limit from 2, or you can simply say x is a member of prime numbers, then you give this limit all the way up to 11. Or if you want, you can simply say x is such that x is a member of prime numbers less than 11, because people, or a person that knows a set of prime numbers, will be able to list, or will be able to tell what prime numbers are there before 11. Okay, so thank you very much, guys, for watching this video. If you found it helpful, please don't forget to subscribe, to like, to comment, and to share these videos with your friends. And if you're having struggles in understanding, or if there's anything that is not satisfactory enough for you, please leave a comment and let us know how you feel.